So I just rewrote him, right? Like that. And now we're using your sum and difference. So that's the sine of the first one times the cosine of the second one plus the cosine of the first one times the sine of the second one. Well, these are the same thing. So like terms, you just add. You get 2 sine, cosine. Yes. Right? That's all I was doing there. Does that make sense? So.
Can you explain tangent on C?
Yeah, so for tangent, you end up with, if you look at your tangent rules, the top one follows and the bottom one doesn't. So we're going to say the tangent of the first one plus the tangent of the second one. That's how we get this guy right here, right? And then it's 1 minus the tangent of the first one, tangent of the second one. Tangent times tangent is tangent squared. So they're just showing you that the sum and difference produce actually another rule, which is what we're going to talk about today. So the next identity that we're going to talk about are the double angle identities. So if you look at your sheet, those should be probably in order next. Double angle identities, as we just saw from the bell work, are generated from your sum and difference identities. So sum and difference is really just a memorization technique, right? You're adding two angles. You have to know for sine, cosine, or tangent how to place those in there. And then you're just really taking the sine, cosine, or tangent and plugging in your numbers. But what happens is you create double angle identities. You'll notice that sine and tangent only have one option, but cosine has 3 options. Those 3 options stem from the first, okay? The first one is what you generated when we did our bell work. Cosine squared minus sine squared. The other ones are generated from Pythagorean identities. So they just took the cosine squared, left him alone, and they changed the sine squared to the Pythagorean identity, 1 minus cosine squared, okay? So all they did to get this second guy is they replaced sine squared with 1 minus cosine squared. And so you have, if I were to write this out, we start with this guy, cosine squared minus, and instead of sine squared, we're going to say 1 minus cosine squared from Pythagorean. Distribute your negative, you're going to get 2 cosine squareds and a minus 1, all right? So then to get the next one, they replaced the cosine squared with 1 minus sine squared. And so they rewrote that guy, 1 minus sine squared minus sine squared, and you can see you get 1 minus 2 sine squared, all right? And so there are different, you really just need to know those top 3 that we generated from the sum and difference. But if you ever forget these, guess how you can get them? Using your sum and difference, right? So we are going to be using these double angles to solve some things. So it's really good to memorize them, but you can at least see where they came from if you were to forget them. All right, so example 1 says, applying the double angle identities. If the tangent equals 3 halves, and pi is less than theta, which is less than 3 pi over 2. Find the exact value for cosine of 2 theta, sine of 2 theta, and tangent of 2 theta. So a couple things here. First of all, you have to pay attention to everything they've given you. It is not unimportant. So the first thing is they told you tangent. You'll notice that tangent is positive. And then they gave you a little bit more information that was way more specific. Theta is between pi and 3 pi over 2. What quadrant did they tell you you were in just now? The third quadrant. So this is important because we need to know that we are in the third quadrant. All right? They want the exact values for cosine of 2 theta, sine of 2 theta, and tangent of 2 theta. You'll notice from your double angle identities that in order to find those, you need to know the sine and the cosine and the tangent. So the tangent's easy. We can quickly find the double angle of the tangent by just simply plugging it in. Okay, the tangent is probably the first one I would tackle because I have all that I need for this. Tangent of 2 theta is 2 times the tangent of theta over 1 minus the tangent squared of theta, all right? And so I'm literally just going to take that guy and plug it in for tangent. Simple, right? So I'm going to say 2 times, well, that's 3/2, over 1 minus 3/2 squared, right? 2 times 3/2, they were nice. They allowed us to get rid of that guy right there. So we just have a 3. This is 9/4. So we have 4/4 minus 9/4. So we have negative 5/4 down here. If we keep change flip, we're going to get negative 12/5. And so we have solved for this first one. We have, and I'll write it over here so we have them all. The tangent of 2 theta then equals negative 12/5. All right, we have that one. Okay. They gave us tangent. There's a couple things we can do here. You can pull any of the identities that we have used so far. They went back to reference angles and angles on the unit circle, which is fine. You can use 1 plus tangent squared plus 1 equals secant squared. And then if you have secant squared, what do you have? You have cosine, right? And so you can use any of your identities that work. I don't think most of y'all would think to do what they did. They went back to tangent is sine over cosine. Those have to be both negative, -3, -2. They found r. So they did any point on the unit circle, which is going way back for us. Your brain may go straight to like a Pythagorean identity here, which is fine. You can do it either way. If you do a Pythagorean identity, you would probably use your tangent squared plus 1. If you do what they did, you're going to have to find your r and do y over r, x over r, and solve that way, which is how they did it. So I'm actually going to use a Pythagorean identity because I feel like in this particular chapter, you're going to be using it over and over on your test. And when you get to this point, you're not going to think to go back to your y over r, x over r. So let's try the Pythagorean identity and see how this works. So if I have tangent and I need to find the sine and the cosine, I am going to use tangent squared plus 1 equals secant squared. And so I'm going to say tangent squared plus 1 equals my secant squared. All right. So again, I have 9/4 plus 5/4. Plus 4/4. Why did I make that 5/4? Plus 4/4 equals my secant squared. My secant squared is going to be 13 over 4, which means my secant is going to be square root of 13 over 2. I happen to know this is negative. Why do I know that? Because I am in which quadrant? The third quadrant. So I automatically know that. So now I actually have my cosine. My cosine is just going to be the reciprocal. So I know what just the cosine of theta is. Cosine of theta then is going to be negative 2 square root of 13 over 13. I rationalized it, right? And so I know my cosine. If I need to know my sine, I can use Pythagorean identity here as well if I want to. I can say, well, I know my cosine. I can do sine squared plus cosine squared equals 1, and I can find out what my sine value is as well, and plug it in. So if I can do it whichever way I want. Also, remember with your cosine of 2 theta, you actually don't need your sine to find it, right? One of your cosine of 2 theta is this guy right here. We have 2 cosine squared of theta minus 1. So if you're just trying to find the double angle for cosine and you have cosine, you don't need to solve for sine. I can actually go ahead and plug this in right here. And I can say that's just going to be 2 times this guy. And you know, I would actually probably leave it like this to square it, because it's just going to get rid of that 13 for me, minus 1. So if I were just finding cosine, I would rationalize it. If I'm plugging in here, I wouldn't. Does everybody see why I would not rationalize it here? Why I would leave my radical in my denominator? Because when I'm squaring it, it's going to go away. And I don't have to deal with 169 on the bottom and 13 on the top and then reducing it. Okay, so I just took the The other, cosine when I flip it is negative 2 over square root of 13. That's just the rationalized version of it. So I did that. So here I'm going to square the top and square the bottom. We're going to get positive 4 over 13 times 2 minus, this is 13 over 13, 8 over 13 minus 13 over 13, negative 5 over 13. So I have my other piece that I'm looking for. Cosine of 2 theta equals negative 5 over 13. All right? Negative 5 over 13. And then my last piece is to find my sine value. You can find your sine value a multitude of ways. You have your tangent, which is right given to you. You have your cosine, which is here. You could say tangent is sine over cosine. You can solve by multiplying those. You can use your Pythagorean identity, sine squared plus cosine squared equals 1. Like there's a multitude of ways to find your sine. However you do it, you're going to end up with a sine value of negative 3 over 13. That's what your sine value is going to be. And so when I'm doing the double sine, I have to first find it. And my sine value is going to be negative 3 over the square root of 13. However methods you solve for it, whether Pythagorean or just reciprocal and quotient identities. And you're going to do the same thing for this guy. We're going to plug it in. My sine of 2 theta is 2 times the sine cosine. And I now have both of those pieces, so I'm just going to plug it in. 2 times the sine times the cosine. So I have 2 times negative 3 times negative 2. That gives me a positive 12. Square root of 13 times square root of 13 is positive 13. So I have those last two pieces help me get the last thing I'm looking for, which is the sine of 2 theta. And so you're going to be having to pull all the things. This is building, as you can tell, right? You're going to have to use some method to solve for sine, cosine if you don't have it. For tangent, if you have sine and cosine, you can literally just put them over each other. I do want to say, had they not given me tangent and had they given me another one, like say they had given me sine, you don't have to use the double angle of tangent if you already solve for sine and cosine. Because if you solve for sine of the double angle and you solve for cosine of the double angle, you don't have to use the double angle formula to solve the rest of it. You can literally put sine of double angle over cosine of double angle because that's what tangent is. Does that make sense? In this case, they gave me tangent first. So it was easier just to go ahead and solve for that when I had it, all right? But if you don't have tangent and you solve for the other double angles, you can literally put sine over cosine to get your tangent piece of it. a triple angle. You're never going to use a triple angle. The reason you're not going to use it is because you can actually derive it from all the others. But let's say you were given something that had 3 theta and you're thinking, I don't have an identity for 3 theta. I have one for 2 theta. Remember, when you add theta, theta plus theta plus theta is 3 theta, right? And so you could break this up and say, well, instead of saying the sine of 3 theta, I could say the sine of 2 theta plus theta. This is going to incorporate your sum and addition, your sum and difference, as well as your double angle is what's going to happen here. And so the first thing you're going to do is use your addition property, your sum identity here. And you're going to say, well, if I have the sum of 2 angles, I can replace that with the sine of the first guy, cosine of the second guy, plus the cosine of the first one, sine of the second one. All right. And then I can replace those with my double angles. Now, the only thing with cosine is you're going to get to a point where you're like, which one do I use? And so, for example, if I had had a cosine here, I probably would have used the double angle that only incorporates the cosine. Because I have a sine here, I'm probably going to use the double angle that only incorporates the sine here. Just to make it a little more simple, reduce however many things I'm multiplying. So my double angle for my sine, I really only have one option there. This guy is reduced with the 2 sine of theta, cosine of theta times cosine of theta. For this one, we're going to do this guy. All right. And you could have done it another way, because you could have had cosine squared as well, if you had wanted to. There is something that is going to happen here that's make this one a little bit unique, because this guy is going to be cosine squared. All right. We're going to distribute here. So we're going to say sine of theta minus 2 sine cubed of theta. And because I have everything in sine, I'm actually going to use something here. What is cosine squared? Another identity. I can replace that with what? Cosine squared is 1 minus sine squared, isn't it? So I can do that again, and I can say, well, let's get this all to sine values. All right, because the instructions are telling me sine values. And we're going to distribute again. We have 2 sine of theta minus 2 sine cubed of theta plus sine of theta minus 2 sine cubed of theta. We're just now going to simplify like terms. So I have a 2 sine and a 1 sine. That is 3 sine of theta. I have a negative 2 cubed, a negative 2 cubed, negative 4 sine cubed of theta. They wanted it all in terms of sine. All right, so they wanted me to simplify that using all terms of sine. All right, so they just, and you would do this potentially if you had just the sine of theta. So let's say they gave you the sine of theta and they wanted you to find sine of 3 theta. Well, you can't just multiply it by 3. That's not how it works, right? So you can't just say, well, the sine of 3 theta must equal 3 times the sine of theta. That is not true, right? The sine of 3 theta actually equals that, which is clearly not 3 sine of theta, because 3 sine of theta is actually in there, and you subtract something else from it, okay? So you can't, it's not like distribution where you can just pull that 3 out. That's not how it works. You actually are doing that process before you do the trig function. We have power reducing identities here. These actually come from your double angle identities, and we're not going to do the proofs for them, but they come from your double angle identities. If you'll recall, actually the sine and cosine come from your double angle. So if you go back to your double angle identities, you can see that cosine or sine squared, if you were to take that out from the 1 minus 2 sine squared for the cosine double angle, you can manipulate it to get the sine squared by itself. And so if I were to take just one of them, if I were to take the cosine of 2 theta equals 1 minus 2 sine squared of theta, if I'm trying to get the sine squared by itself, I'm going to subtract 1. So I have, and actually they're moving the negative out. So move the 2 sine squared of theta over here, move the 1 minus cosine of 2 theta over here, and then divide by 2. All right, so all they did was take the double angle and manipulate it. They took the double angle and they solved for sine squared, all right? They did the same thing with cosine squared. They took the 2 cosine squared minus 1 of the double angle and they solved back for cosine squared. And then you'll notice tangent squared is just sine over cosine. So this one, if you don't remember it, you can put this over that and you'll have the same denominator, right? Sine over cosine, denominators cancel, and you end up with numerator over numerator, numerator over numerator. So the tangent is just the numerator piece of the sine squared over the numerator piece of the cosine squared, right? So if you ever forget your tangents, you can literally just use the sine over the cosine, all right? Reducing the power. So, and we're gonna do some problems where we have to use some of these. So reducing the power, they give you something like this, sine to the 4th, and they want it all in terms of less than 2. So pretty much nothing greater than 1 power here is what they want. And so when you have something like this, obviously we don't have a sine to the 4th, but we do have a sine squared. And hopefully from your exponential properties, you remember that those are the same thing. All right, and that helps us only because we have a property or an identity for sine squared. And so we're going to replace our sine squared with our property for that guy. All right, I do want to point out, when you have a binomial, you have to FOIL it. The most common mistake is people do the 1 squared and the cosine squared. You have to FOIL it, all right? And so when you FOIL this, you end up with 1 minus 2 cosine of 2 theta plus the cosine squared of 2 theta. You have to FOIL that guy. And of course, the denominator is just 2 squared, which is 4. All right. Now, I will say, in something like this, I would actually pull that denominator out because all I'm trying to do is get it with no squares in it, right? Pretty much. So the first term here obviously does not have a square in it. The second term doesn't have anything to the second power. I just really need to deal with him. And so getting these guys out of fractions is going to make my life a little bit easier at this point. So I'm just going to put each numerator piece over the 4. So I'm going to put the 1 over the 4 minus the 2 over the 4. So that's 1/2 cosine of 2 theta. Plus, and then that's a 1 in front of that, 1/4 cosine squared of 2 theta. So I'm going to do something like that, right? Because I don't want to have all those fractions in there to deal with when I really only have to deal with the last term, all right? And then we have something for cosine squared. So I'm going to replace this cosine squared. Now pay attention to what happens here. I'm going to leave these alone for right now. Cosine squared, this is my new angle, right? 2 theta is my new angle. And so when I plug it in here, I have to remember I'm saying 2 times 2 theta. So I'm going to replace the cosine squared with 1 plus the cosine of 2 times this guy. That's 4 theta. Everybody see that? Right? Because I already have a 2 theta as my angle, and I have to multiply it by 2. And then that is over 2. All right. And then I can just simplify that, right? I'm going to do the same thing here, like 1/2 plus 1/2 cosine of 4 theta, like that. That way I can get my fractions together. So if I were to do that, I would rewrite this, leave the first guys alone for right now. and we're going to leave this alone, 1/4 minus 1/2 cosine of 2 theta plus, and I'm going to distribute this 1/4 through. So 1/4 and 1/2 is 1/8 plus 1/8 cosine of 4 theta. The only thing I can combine here are my fractions. All right. The reason is these two have different angles. This is a 2 theta. This is a 4 theta. So I cannot combine these because they're different inside, right? And so I can really only combine my fractions. They did it differently. They actually pulled a 1/8 out of everything. I don't think you're going to think to do that. Just leave it as fractions. It's fine. I don't think you're going to think to pull out a common denominator. It's not something people typically think to do. So you can just combine these. This is 2/4, right? I mean 2/8 and 1/8. So you can just say 3/8 minus 1/2 cosine of 2 theta plus 1/8 cosine of 4 theta. You're welcome to leave it that way. If you look in the book, all they did was factor out a 1/8. That's what they did, okay? But again, most people aren't going to think to do that. It's fine, all right? You can leave it like this. You don't have to factor out a 1/8. All right, the last one we're doing is half angle. We're actually going to solve using this because the reason you do half angles is when you have like something that is close to something on the unit circle. The example that they give us is pi over 8. Well, pi over 8 is not on the unit circle, but pi over 4 is. And so if I were to take pi over 4 and divide it by 2, that's pi over 8. And so then you can say, well, I know the cosine of pi over 4, right? I don't know the cosine of pi over 8, but it equals this. And so you can have an angle that if you were to cut it in half, it would be an angle. I mean, if you were to use the angle and cut it in half, it'd be the angle you're looking for. And so this is when you're trying to use a unit circle angle to solve for an angle that's not on the unit circle to find an exact value versus a, never-ending decimal value. All right. And so again, these are ones that you're going to want to memorize. They do, if you notice, they do stem from the squares. Hopefully you recognize these, like they stem from and they look very similar to the squares. You just don't have the double angle, and that's coming from combining the double angle and combining the sine squareds. That's also why you have a positive and negative answer. All right, so the positive and negative answer is what's going to change that. But you'll have to think about where your angle lies to decide which one of those you're going to use. You're going to have to say, what quadrant am I in? Do I use the positive? Do I use the negative? So let's look at just one of these. We're just going to do the sine because it's kind of repetitive. All right, so we have pi over 8. Pi over 8 is not on the unit circle, okay? And so I'm going to try to look for something that I could cut in half or I could double to get to pi over 8 because now I have double angle and I have half angle identities. Okay, does that make sense? And so there's nothing that I could double, right? If I multiply by 2 necessarily that I'm going to be able to get pi over 8 because that would be pi over 16, right? Pi over 16 is also not on the unit circle, but pi over 4 is. And so if I think about this in terms of what I could double or what I could half, I'm going to say, well, if I took pi over 4 and cut it in half, that would be pi over 8. Everybody see that? Right? And so now I'm going to say, well, I am going to use my half angle identities. I'm going to say, I'm going to solve for this guy by rewriting him like this. Sine of pi over 4 over 2. And I am going to use my sine of theta over 2. All right, theta being the pi over 4. Okay? And so now I'm just going to plug it in. My half angle for this is going to be positive or negative, right? Square root of 1 minus the cosine of my theta. Well, my theta is my numerator, so pi over 4, all over 2. Now, if I'm trying to find the sine of this guy, I have to decide where he is. And then I can forget that positive, negative. I can go ahead and figure that out, right? So I'm going to look at this and I'm going to say, where is pi over 8? What quadrant is pi over 8 in? Well, he's smaller than pi over 4, right? He's in the first quadrant. So what is the value of my sine, positive or negative? So do I even have to put plus or minus there? No, I can go ahead and determine I am only going to use the positive square root here because I'm solving for sine. Sine in the first quadrant is positive. And then I'm just plugging it in. I'm going to say the square root of 1 minus, what is the cosine of pi over 4? Square root of 2 over 2, all over 2. I would simplify this guy before I try to do any roots here because it's going to be a hideous root, by the way. So my common denominator on the top is 2. So I end up with 2 over 2 minus square root of 2 over 2. So 2 minus the square root of 2 over 2 over 2, right? Everybody see what I did there? I just got a common denominator for this top piece right here, right? Common denominator, 2 over 2 minus square root of 2 over 2, okay? And then the whole thing is over this 2. How can I simplify this? Well, denominator over denominator, what happens there? That just becomes 2 minus the square root of 2 over 4, right? And then, believe it or not, this is going to be your answer. The numerator does not have a perfect root, so the numerator is going to remain like this. Isn't that beautiful? The denominator does have a perfect root. What is the perfect root of your denominator? 2. We've already determined we're in the first quadrant, so we're going to use the positive root. We're done. That's our answer. Why does this help me? Well, if it wanted me to solve for the angle here, I have a problem. I have the cosine of the double angle. The sine of the double angle and the cosine of the angle. This is an issue. If I am solving for an angle, they all need to be the same angle I'm solving for. It's like having x and y in an equation. You have to rewrite one as the other, right? If I have x and y in an equation and I'm trying to solve for it, I need to eliminate one of those variables. Because if not, I can never solve for it. I don't have enough information. This is what we're doing here. If I have a double angle, I need to rewrite it so that it's not a double angle. Either they both have to be double angles or they both have to be just the angle, right? And so in this case, I'm going to say, I'm going to rewrite this guy. Like, he doesn't help me. And so I'm going to rewrite him using my double angle. And so you're going to have to go back to your double angles and say, sine only has one of them. It's 2 sine cosine, right? And so I'm going to rewrite him instead of sine of 2x. I'm going to say it's 2 sine x cosine of x. And now I have an actual rather simple equation I could solve, right? Subtract your cosine of x over. Factor it, factor out that cosine. And then set each factor equal to 0. Where is your cosine 0? Well, your cosine is 0 at pi over 2 and 3 pi over 2. Setting this equal to 0 is where is your sine equal to 1/2? Well, that's my 30-degree angles in the first and second quadrant. And so that's going to give me pi over 6 in the first quadrant, 5 pi over 6 in the second quadrant. And I've now solved that. Whereas before I wouldn't be able to, right? And so you can plug these in to solve. The same is true with half angles. With half angles, look at this guy. This doesn't help me. The angle that I'm solving for, one of them is pi x over 2 and one of them is x. I can't have that. That's not going to help me, all right? And so with this one, it's not as easy to see what's happening here because Cosine of pi over 2 actually puts it in the root, right? But you can square it out of the root. So if I look at my half angle for cosine, right? My half angle for cosine, I'm going to get the 1 plus cosine of theta. Right? And that is in the root. It is positive and negative root. But now at least I have them in the same terms, right? They're both the same variable that I'm solving for. And you do exactly what you would do. Get rid of your root, right? Get rid of your root, squaring it. We have 1 plus cosine of x. If you square a root, it's automatically positive. All right. And again, now I'm going to go back and say, okay, I have them a sine and a cosine. What can I do to get rid of that? Well, you can get rid of that using Pythagorean identity, right? This is 1 minus the cosine squared of x, right? And then I can multiply both sides by my 2. I can move everything to one side and I can factor this. Does that make sense? So I can move these over. 2 cosine squared of x plus the cosine of x. Subtract your 2 over minus 1 equals 0. Factor him and solve, right? So now I can factor this guy, set each factor equal to 0. Where is my cosine 1/2? Where's my cosine -1? And all of a sudden I can now solve this. So cosine is 1/2 in the first and fourth quadrants for my 60-degree angles. So that's pi over 3 and 5 pi over 3. And then cosine is -1 only one time, and that happens at pi. All right. And so you can now use these double angle and these half angles to solve for the x's, whereas prior to this, you wouldn't be able to because it's like having two variables.